Hello students. So we have the basic idea behind inclusion-exclusion. It's for situations where you have a union and you want to compute the size of it, or you want to get rid of a union. We want to count everything that's not part of a union. Maybe you have a list of properties that you're trying to avoid, and if any of those properties happen, we want to not count it. So we want to basically subtract a union. For example, if we have 3 sets, this is what the size of the union would be like, and we saw this in the last video. I want to generalize this to more sets and come up with maybe a nicer formula. Okay, so one way to do this is we could say, hey, the number of elements in S, where S could be any subset, and we're sticking to 3 sets just for now. The n of S is going to be the number of elements which happen to be in the intersection of all of the sets in S. So for example, n of 1, 2 would be the intersection of A1 and A2. And n of 1, 3 would be the intersection of A1 and A3. And n of 1, 2, 3, well, this would be the intersection of A1, A2, and A3. Okay, so now I might have a better way of writing all of this down, because I can see what this is, this union is. It's going to be all the subsets of size 1, we're adding. We're subtracting all the subsets of size 2, and we're adding all the subsets of size 3. So I want to express this as a single sum. Okay, and I want to take all the sets S in 1, 2, 3. that are not empty. I don't want to take the empty set. The empty set, I guess, would be the whole universe, all possibilities. We're not constricting to an intersection of anything. So, but notice that doesn't appear anywhere here on the right, and this is what we're trying to compute. So we don't want the empty set to be a set. But every other possible intersection does. Okay? So what I'd want here is I'd want something to determine whether things are positive or negative. I'm going to leave that exponent blank just for a moment. And then this is times n of S. Okay. Now we want this to be negative when the size of the set is odd. So what I could do is I could say size of S plus 1. I could have also said size of S minus 1. And what is this equal to? Well, this is equal to the size of the union. So the size of A1 union A2 union A3. Okay. Now, of course, this extends to any number of sets once you've written it like this. So what I would get is, if I wanted the size of this, let's go all the way up to M, this is going to be the sum of all S in 1 through M, and this is going to be minus 1 to the size of S plus 1 times the number of elements that are in that intersection for S. And this is the full formula. Now there's 2 versions though. I said sometimes we want to include and sometimes we want to exclude the union. So this is one way of writing the inclusion-exclusion formula. And there's another way of writing it when we want the things that aren't in. Suppose you want the things that aren't in. Well, then what we really want is we want this minus this whole thing. I'll just say minus the right-hand side. Okay? Okay. Well, if I'm subtracting the right-hand side, I could say what I want is this. And I'm going to multiply all of this by negative 1 and add it. So basically, I get this. So I could just make this minus 1 to the S. Because minus 1 to the S plus 2 is the same, size of S plus 2 is the same as minus 1 to the size of S. So now I'm in this situation, but notice something. I've ruled out the empty set here, and I want to add the empty set here. And if I just get rid of this, I would automatically be including the empty set over here, and not only that, I would have the correct sign, because the empty set has 0 elements, And what is the size of the empty set? 0. So I get minus 1 to the 0, which would make it positive, which is what I have here. I have a positive n of the empty set. So this would be equal to just this without that empty set there. And this is a very nice formula. So I have to say what this counts. And what this counts is it's going to count the number of elements that aren't in any of our sets, or that meet none of our properties. Where A1 is the set of elements that meet property 1, and A2 is the set of elements that meet property 2, and so on. And this even looks a little nicer than this. I mean, it doesn't have that. It doesn't have the plus 1. So this is sort of formula that we're going to be using a lot of the time. And quite often what we really do want is we want to exclude things that have any number of properties from some collection of bad things that we're trying to avoid. So this is the inclusion-exclusion formula. Or this, depending on which version you want. This is the one where you want the union. This is the one where you don't. Now, you might say, oh, this looks very pretty mathematically, but this might be more the way I think of it, right? And in that case, that's fine. You could just go up to 4 sets in the union by saying, hey, A1, A2, A3, and A4, and then you'd subtract the intersection of any 2 and add the intersection of any 3 and subtract the intersection of any 4. And you could go further with this as well, if we wanted to. As long as you're getting every possible combination of 2 sets and every possible combination of 3 sets, and so on and so forth, you'll still be getting the same, just a different way of writing the same formula.